Hi, everyone. We're going to talk a little bit about an introduction to the meta-analysis now. So you've done your literature review, you synthesize the findings, and you discover that you have a handful of randomized controlled trials that you could combine. And nobody's conducted a meta-analysis on this topic yet. So that's what we're going to go through now. I'd like to say a special thank you to Dr. Choi, who is a former colleague of mine at Arizona State University, who provided this example for us. She conducted a meta-analysis on some studies related to falls in elderly. So we'll talk about her work here in a minute. So the objective here today is to understand the process for meta-analysis, discuss the steps to performing a meta-analysis, and then review some meta-analysis results. So what is it? It provides a systematic overview of quantitative research, and it combines several studies on a relevant topic of interest. It statistically helps you draw conclusions about the results or the overall effect size of multiple studies by statistically combining them, and helps to define or identify what questions have already been answered and which questions still need to be have further investigation. So why is it used? Grant agencies frequently encourage investigators to use a meta-analysis to justify the need for a new study. If they've already funded 6 RCTs and they've all found the same thing, they're not going to want to spend money to investigate that further. Pharmaceutical companies also use meta-analysis to gain approval for their drugs, and it helps us draw conclusions about studies with small sample sizes or studies that have mixed results. Maybe one says an intervention works and the next one says it doesn't. Well, how do you draw conclusions about that? So this is a way. So Dr. Choi, my former colleague, conducted this study. She wanted to look at the last 10 years worth of research, randomized controlled trials on a falls intervention for elderly. And so she wanted to know, her question was, what's the overall effectiveness of fall prevention programs that are used? So the process is to outline the objectives, which we just talked about, establish the research criteria. So her criteria were falls, elderly. She wanted to know for both males and females. And she wanted the outcome measure of relative risk. And we'll talk about that in a while. But what you're going to do in this class is actually learn how you can use odds ratio, relative risk, effect size. Things can be used interchangeably in the meta-analysis calculator that we've provided for you in the course. And her other criteria was that it was a randomized controlled trial. So the process moves on to data collection, and you identify the studies, you'll assess the quality of the articles you've chosen, and you have 2 independent reviewers who then meet and talk about the discrepancies, and then you analyze the combined data quality. So this process of establishing the research criteria really narrows down your search. It eliminates unnecessary time and a real consuming, unnecessary waste of time in this process by being real clear about which studies you want to include and which ones you don't. And then it reduces confusion around what is it that's really the focus. And co-investigators need to agree up front what the criteria are going to be for inclusion and exclusion. So here's an example of the research criteria that she used. the effectiveness of fall prevention programs. So she wanted randomized controlled trials, elderly, which she defined as 65 years and older, studies including both males and females, had to be about the intervention fall prevention program. They excluded Asian studies, and the intervention needed to be 6 months or more, and the outcome measures used were relative risk and the number of falls. So the data collection is the process of identifying the studies. So again, you have at least 2 investigators search the relevant articles. Use reliable search engines. You can use PsycInfo, CINAHL, PubMed, Medline, ERIC, Gister, RefWorks. Those are all useful. And as I've said over and over in this class, I highly recommend working with a medical librarian so you don't miss anything. You want to use consistent keywords throughout the searching process. And here's her keywords, which we've talked about already. And you want to go through them after you've done the search, read the title and eliminate irrelevant articles, read the abstract to see if it meets the criteria. And they had decided they wanted only RCTs, so they excluded non-experimental studies, observation, longitudinal dissertation data, and quasi-experimental. All those were left out. You read the methods to see if the outcome measures are consistent with your criteria. So many studies now will actually include an effect size. In her particular study, I think they just used the risk ratio or odds ratio, number of falls, correlation, and mean difference. Record the number of articles from each search engine. Eliminate overlaps. Read the entire article if they meet your criteria, and they found less than 30. And meet your co-investigators to decide the final articles to include for meta-analysis. So just a few words about this odds ratio and risk ratio. And this is an example of what we're looking for with the odds ratio and the risk ratio. So the odds ratio is used with case control studies, and the relative risk is used with cohort studies. So as we look at the odds ratio, it's an estimate of the relative risk in a case-controlled study. So in this particular example, as you look across the top, the disease is lung cancer, and it's either yes or no. And the risk is smoking or non-smoking. And your smokers, as you do the odds ratio here, your smokers were 24 times more likely to have lung cancer if you use the odds ratio. If you use the relative risk, it's an estimate of the magnitude of the association between the exposure and the disease, indicating the likelihood that the exposed group will develop the disease relative to those who are the non-smokers. So in this particular case, we have the 0.20 as the relative risk, which means that non-smokers had a decreased risk, 0.2 less likely than smokers to develop lung cancer. So this is just a flow chart of how you select the studies to include. And this is included in most publications of meta-analysis and is really an important process to outline. So when you're doing the searches, you want to keep all those numbers. So in this particular example, she had 17,000, over 17,000 titles and abstracts were generated from her search. And then after she went through them, she found that 15,000 could be excluded because they, either the title or the abstract really didn't look like it was relevant. And another 1,600 were excluded because they weren't RCTs. So that left her with 287 potentially relevant studies. And they excluded falls in children because that's not what they were after. And they excluded all the duplicate studies. And so then they were down to 227. And then they eliminated studies that didn't report fall intervention or effectiveness of the program. And they also excluded unclear intervention periods or didn't meet the requirements that they had set, or if it was a quasi-experimental design. And 15 studies were excluded because it didn't include both men and women. So now they're down to 21. And the studies that were completed in non-Western countries were excluded, so that was 4, and that left them with 17 studies that they included in their meta-analysis. The next step now is to assess the quality of the studies, and again, this is done independently with 2 investigators separately doing the assessment. And they use 2 different assessment measures. They use the Downs and Black checklist, and it measures inter-rater reliability among 2 or more raters. It consists of a total of 27 items and 5 subcategories, and you just go check down yes or no, it had it or it didn't. And so there's 10 items for reporting, 3 for external validity, 7 for internal validity, 6 for selection bias, and 1 item for power. And these are the individual items, and certainly you can look up if you really want to see the specifics of this, but you can see, you just say yes or no or unable to determine for each item. And then you get together after you've completed it for each study, and you look for agreement, and we'll go into that a little bit more in a minute. What they did for this particular study is they also used the JDAD scale, so they assessed for quality with 2 different measures. And the JDAD scale looks for methodological qualities of clinical trials, and it's a 3-point questionnaire, measures again, yes, no. Was the study randomized, double-blind, and was there a description of withdrawals and dropouts? So with that information now, the 2 raters come together and examine the extent of consensus on the use of the scales. And raters need to be completely blinded to the other person's findings until they meet to check consensus. And what you actually can do is run some correlations in SPSS, either the Kendall's W coefficient if you have more than 2 raters, or the Cohen's kappa if you have 2 raters, and it'll tell you the degree of agreement between the 2 raters. And this one is a kappa of 0.796, which is, 80% agreement is really, really high, and that's good, so they just moved on. And this slide just gives you some meta-analysis software if you decide you want to do this in the future. But for the purpose of this course, the meta-analysis calculator in the Canvas shell is adequate to do the analysis assignment. And we just have the formulas programmed into Excel. So it's a very simplified version of conducting a meta-analysis, and that's what you'll use for your assignment. So what are the terms used in meta-analysis? We talk about the effect size. That's the magnitude of the treatment effect. It's the strength of a relationship between the two variables, the treatment and the outcome. And there's a standardized mean difference. So the p-value of the effect size is less than or equal to 0.05. The Hedges G is something you may see as you're reviewing articles, and it's bias-corrected standardized mean difference. The Q statistic you may see as well. It's a measure of a weighted square deviation. The p-value of the Q statistic is greater than or equal to 0.05, so the opposite of your p-value for the effect size. And the tau squared is the between studies variance. So it gives you the between studies standard deviation and the standard deviation of true effects. The I-squared is the ratio of true heterogeneity to the total observed variation. And you want to know about the heterogeneity of the effect sizes. So did every study find the same effect, or was there a big variation in that? And then subgroup analyses are sometimes also reported. If the I-squared is large, subgroup analysis is needed so that you can understand the reasons for the variance. So as we said before, the p-value less than 0.05, remember that you're going to reject the null if your p is less than 0.05. And that means that there's a 5% chance of rejecting the null when in fact it's true, and that's your type 1 error. There's a 95% chance that the difference you observed reflects a real difference. And then if the p is greater than 0.05, you're going to accept the null, and you have a 5% chance of accepting the null when in fact it is false, and that's the type 2 error, but you have a 95% chance that the difference you observe reflects no real difference. The confidence intervals are usually reported as well, and it's the reliability of the estimate. Usually a 95% confidence interval is what's reported. And that just means that you can be 95% sure that the confidence interval includes the population mean. Make sure the sample mean falls in that 95% confidence interval. The other thing that meta-analyses usually include are an assessment of publication bias. And you can do that with a funnel plot, or you can do it with additional statistics. And that's a sensitivity analysis. So it's used to see how the results change if a different study was included. And it tells you if there was a different effect size and adjusted means versus raw means. So that just gives you a little more information. And in the assignment that you're going to do, we're going to ask you to calculate how many additional studies might be needed to change the conclusions you draw from that meta-analysis, and that's called the file drawer test. The interpretation of your pooled results are important now as you're reading the meta-analysis. You want to know what that combined effect size based on the risk ratio and the confidence intervals are calculated for each individual study and then combined. And the combined effect size of the risk ratio for the 17 studies was 0.847. And that's a p-value of 0.005. And the overall results indicated that the intervention across the studies were effective by demonstrating a 15% reduction in falls. So you've got 17 studies, they agree, it's a strong effect size, and a significant reduction in your falls. So you don't need to do a lot more research in this area. Something else you'll sometimes see in publications of meta-analysis is a graph like this with each individual study and the p-values for the individual studies listed. So here's your p-value, here's your risk ratio, and here's the intervention, the control, and you can see that most of these, each of these squares represents one of the studies, and this is the mean, and this is your standard deviation, the line that goes, tells you. But you can see that for the majority of these studies, it looks like there's a reduction in the number of falls. So the sensitivity analysis, as we talked about a minute ago, determines how the results would change if studies were removed from the analysis. So you remove the studies based on the quality assessment, or you can do a random standard residual, or based on your own reliable rationale. You remove one study at a time to see how this affects the results. So let's say you assessed of those 17 studies, 2 of them seemed like they had a pretty weak design, so you might start with those 2. So when they did this, they then had 13 studies of pooled results. And as you can see, they still continued to show things hovering around the 1 for falls, but your p-value is no longer significant. It's now at 0.06. So the risk ratio is 0.84 with your p of 0.000 with a 95% confidence interval, demonstrating there was a significant 16% reduction in falls across the studies. And these 13 studies were found to be homogeneous, so they found the same things. And there's your p-value that has no, it's not a significant difference in the Q statistics. So that demonstrates that there's no variation across the studies. So there were significant reduction in risks of falls, and there was not differences in findings between studies. So the results of this meta-analysis indicates that the RCTs of fall prevention programs described within the last 10 years really showed that they were effective, and they focused on multifactorial interventions and programs performed in the community. And when these interventions were conducted with 12 months or more follow-up, the results looked very positive. And so you don't need to do more research on that topic. The answer is there in those multiple studies. And she provided lots of references for you if you're interested in falls in elderly. And I want to just reassure you that the meta-analysis assignment that we're asking you to do for this class is very simple compared to this example. So don't get worried.